is Bruno Olshausen from the Redwood Center.
Thanks. Right, I'm going to tell you about some new work I've been doing in the lab with students Yubei Chen and Dylan Payton. And this is my first time kind of going into this work in more like detail, revealing all the nuts and bolts of it. So I'm kind of nervous. I've never done this before. So hopefully it comes through. And so first I want to just introduce the people who were helped me do the work and whose ideas I'm largely speaking about today. And that's namely Yubei Chen, who's sitting right here. And he's going to be, well, sort of filling in as questions come up too. And Dylan Payton, who's also been working on this project. And the larger group here is the Redwood Center for Theoretical Neuroscience here at Berkeley. We're based in Evans Hall and started as the Redwood Neuroscience Institute in Menlo Park with Jeff Hawkins, and moved here in 2005. And we're basically a group of faculty, postdocs and students, many with backgrounds in math and physics and engineering and neuroscience and vision science, and trying to bring ideas from these different fields to bear on trying to understand information processing in the brain. Very much like this program here. And so I'd like to start by also, like in Jeff's talk, including a quote from Francis Crick, but sort of a different nature. And I think this kind of gets at an important question, which is kind of a thread in this meeting, which is, are there sort of underlying principles that we can try to get at here in the system? And not everybody believes this. And that's sort of, embodied in this quote here. And to counter that, this quote by Horace Barlow here I think is very interesting. So here he is in 1972. This is his sparse coding paper. And he's looking back at the work of Hecht, Schler, and Perrin in the 1940s and his own work in the 1950s, trying to characterize the efficiency of phototransduction and detection in the retina. And this, what he was showing here is that, initially before people really understood the mechanisms there, they thought that neurons in the retina were noisy and erratic and so forth, and sloppy, and just sort of biology was kind of, a hacker, I guess. And after they understood the actual mechanisms, they could show that the variability in individual observer judgments in light detection could be mostly accounted for by just the variability in the world, the quantum fluctuations of light, and also in terms of known sources of variability in the retina and phototransduction, the spontaneous isomerizations, or the so-called dark light in the retina. And so when you took all these into account, it looked like neurons were actually extremely precise in what they could convey. And I think this is an important lesson, because whenever we sort of come along, it's easy to sort of look at these neural mechanisms or things in biology and say, oh, well, that's a stupid design. That doesn't make any sense. But there's a very high bar to cross, because you actually have to claim to know all the constraints that need to be satisfied, all the issues that are at play there, to be able to make that determination. In many cases, I think we've seen this happen, where things that we didn't really understand turned out to be very elegant designs. And I think one example we could point to is just simply the design of eyes itself, the design of the eye. This is something where biology actually had to work with the principle of optics, and we look at all these different eye designs across the animal kingdom. We can make sense of them in terms of principles of optics. Okay, so that's what the sort of lens through which I'm going to try to view the system today, is that very similar to how there are principles of optics that can help us understand eyes. There are similar principles that could help us understand what this circuitry is doing here. And so the way I'm going to be trying to approach this sort of the stuff I've been doing in the lab for a long time, is trying to understand what's going on here in terms of unsupervised learning principles. And the idea of using unsupervised learning is not so much as a principle of neural development, but more as a way of trying to understand the system, what the system is doing in terms of underlying principles of optimal coding principles. And the idea is that what neurons are trying to do in this system is they're trying to make explicit, they're trying to reformat, take the data that's coming in and reformat it so as to explicitly represent underlying causes, or the things that are actually going on in the world. And information about how to do that is contained in the statistics of the data coming in. So this is sort of what Barlow had a quote, what he said, that is that redundancy provides knowledge. So in the redundancy in the data, in the statistics here, is information about how to organize it and how to sort of pull it apart and extract these underlying causes. Okay, so and this is, I think, where we very much need principles, because a lot of these boxes in this diagram. This is, by the way, this is a nice redraw of the Fellman and Van Essen diagram of visual cortex, where the sizes of these boxes are drawn. The area is drawn so as to reflect the actual amount of surface area that's consumed in the cortex by these different areas, and the lines between the boxes, the thickness of those lines reflects the amount of white matter, or the amount of wires connecting those areas. Okay. And so you can see, like the boxes here, like V2, it's just simply, I would say it's still kind of a black box in the field in terms of what it's doing. I would also call V1 mostly a black box as well, in terms of trying to understand what's really happening in this system. And so this is, I think, where we really need principles to guide our thinking about what could be going on. And so three principles I'm going to appeal to today. These are the three principles I'm going to try to appeal to today for trying to understand the system. And this is more or less the outline of the talk. So the first is this idea of sparse coding. And we're just leading to this idea of feature selectivity, which I think most everybody is familiar with. But the second is this idea of manifold flattening or manifold learning. And that's a way of getting equivariance. So most people are familiar with this idea of invariance. And so I'll use my prop, which is a paper cup instead of a thermo cup that Jeff had yesterday, right? So the idea of invariance is simply that as objects move about in the world, that you have a population of neurons in your brain whose firing is relatively constant, irrespective of the specific pose or transformations of the object. So equivariance is really the flip side of that, is that there's a population of neurons which change proportional to the transformation applied to the object. So as the object moves through the world, there's a population of neurons that increase their activity as it moves one way, or as it rotates in another way, there's another population of activity that changes activity proportional to that transformation. So they're coding for the transformation, not for the object per se. Okay, so it's like the flip side, the flip side of invariance. And so I'm going to argue that this idea of manifold flattening, this is related to ideas that Cox and DiCarlo have talked about, of something that the cortex might be doing. And then a third idea is this principle of persistence or slow feature analysis, like Lawrence Wiscott has talked about, and leading to invariance. And so what I'm going to show here is that these two ideas of sparse coding and manifold learning are intimately intertwined, okay, and that they basically can be thought of jointly together. And that's something that kind of is a new aspect of our work, and something that was a kind of surprise to me initially, that Yubei pointed out. And then finally, that this idea of persistence can be used as a way of learning how to embed the dictionary of a sparse code into a manifold. Okay, and finally, I just want to say that maybe this idea, the overriding principle here is that we can sort of establish short-term objectives for what might be going on in the system, rather than appealing to the end task, sort of doing end-to-end learning and trying to judge the overall performance of the system, which is very unwieldy in terms of backpropagating derivatives and so forth, that we can write down something that, this sort of something not as sort of as lofty as the entire task, but short-term objectives in the system at early stages of the system that the system can use to self-organize its representations. Okay, and this is an idea that was proposed by lots of different people in the field, but a paper that was very influential on me was this paper by David Field entitled, "What is the Goal of Sensory Coding?" All right, so the title is very provocative, and the idea is, that you can establish, can you really write down a goal of sensory coding in the system beyond just saying, well, the goal of sensory coding is to promote the survival of the animal or something like that, right? Can we write down a more specific objective for that in terms of how it organizes information? Okay, so that's the spirit in which we're kind of approaching this. Okay, so let's go first of all into this idea of sparse coding. And so this really all started with this guy here in the lower right-hand corner, Horace Barlow. And this is a picture from the Ratio Club, which was a group that met in Queen's Square, London, through the 1950s, and was basically a collection of, like this brain and computation program, a collection of neuroscientists, early computer scientists, information theorists, who were trying to bring ideas from these different fields to bear on understanding the brain. So the computer scientists in the room will recognize this character here. This is William Rushton, Giles Brindley, Tommy Gould, Donald Mackay, David Mackay's father, and many others. So basically all these different neuroscientists and computer scientists in the 1950s who were doing then what we're trying to do today. Okay, so it's really very interesting. And so these ideas were very influential on Horace Barlow at the time. And Claude Shannon came to this group and gave a lecture on information theory. And that was very influential in ideas that Horace Barlow developed. So he had this paper in the early 1960s on redundancy reduction. And this later paper in 1972 is where he sort of first lays out this idea of sparse coding. Okay? And it's simply stated here that the idea that the sensory system is organized to achieve as complete a representation of the sensory stimulus as possible using the minimal number of active neurons. And so he's basically proposing this as a way of making information explicit. Okay, so the idea is that when you do this, when you take the information and push it into a higher dimensional space and make neurons more selective, it's a way of making that information more explicit about what features are present in the stimulus and essentially easier to read out. Okay. And so there's a couple of things that motivated this hypothesis to him. One was his own observations that as you sort of probe deeper into the system, that neurons tend to become progressively more silent. And it's not clear now, looking back on that, whether that was simply due to anesthesia, that as you go deeper into the system. And so Rest and DiCarlo have looked at this more systematically and shown that it doesn't really so much increase as you go up the ventral stream. But nevertheless, these representations tend to be highly sparse. And the other is that you have this very high degree of overcompleteness in the visual cortex. So what this diagram is simply showing to scale is the number of neurons in the input layer. So this is layer 4C, this portion here. And each of these circular outlines shows the outline of a cell in a Nissl stain. So the number of neurons in the input layer of visual cortex as compared to the number of fibers coming in. So each of these dots here represents a different fiber coming in from the LGN. Okay. So what you can see here is the system is definitely not doing dimensionality reduction in the traditional sense. It's not an information bottleneck in terms of having to do compression through a small number of fibers. It's doing dimensionality expansion. It's taking the data coming in and it's pushing it into a higher dimensional space. Okay, so one idea here is that the same time you're doing that, you're making it more sparse. Okay, so it's a nonlinear transformation that takes this relatively dense activity that's coming here on the LGN fibers, pushing it into higher dimensional space and making it more sparse.
Bruno,
yeah.
Just on the use of dimensionality, it's certainly recasting it in a space with many more variables, but are you also saying that it's transforming the data so that in some linear or other approximation it actually subtends a higher dimensional volume than it did?
Okay, yeah, good question. So I think the idea is that no, it doesn't occupy the whole volume, right? So it's a higher dimensional space. Most of that volume is empty because it's sparse, meaning that, so if you think about the axes of the space, right, it's spending most of the time along the axes and not very much time in the quadrants, okay? But nevertheless, in the sense of sort of linear redundancy reduction, if you did PCA of the space, you'd find all the eigenvalues are essentially significant, right? It's sort of like you have sort of equal amounts of variance in all directions, okay, as you look, but there's definitely not, the volume is not filled. Okay, but it's not sort of just falling in a linear subspace. Okay, so it's pushing out along the different axes. All right. Okay, so this is the idea that Horace Barlow kind of laid out, and so there was a long time between that and then when people actually sort of took that idea and tried to test it quantitatively using natural scene statistics. And this is one of the ideas that David Field first started looking at in the late 1980s and early 1990s. And then when I started working with him, we developed this model to try to look at what if we adapt a model of the cortex, say just sort of hypothesize that what the cortex is doing is it's trying to explain the incoming data in terms of a set of sparse underlying causes. So this is the basic idea here. The image data is coming in, so this is the intensity as a function of space. And you have a population of neurons in the cortex. These are individual neurons, and their activities are trying to explain what's coming in terms of a small number of active units. Okay, so that if you look at this population of neurons at any given time, most of them are going to be silent and only a small fraction are active, and which neurons are active changes from one time point to the next. So we can write down that mathematically here, just as a generative model. They are trying to explain the image data in terms of a set of underlying features, so each of these phi sub I lives in the same space as the image. Think about a local patch of neurons analyzing like a local patch of image. This will be like a 16 by 16 pixel image patch. Okay? And we're going to try to adapt these features here so that we can represent this data as sparsely as possible in terms of these neural activities. So each of these a sub i's is a coefficient from one of these basis functions or features, and we take those to be the activities of individual neurons. Okay, and okay, so what makes this non-trivial is when there's structure in the input. If this were just white noise coming in, this would be a completely uninteresting and not very well posed problem. Okay, but if the data coming in has some structure to it, this is a way of learning about the structure in the input. Okay, and okay, so you'll notice in this equation that the activities of the neurons are on the right side of the equation, and the data coming in is on the left side, right? So what we need to do is get the a sub i's over to the left and the image data on the right side. And the way we do that is by writing down an energy function of the system. And this is basically an objective function, both used for learning, but primarily for determining the activities of the coefficients. Okay, how do you compute these coefficients in response to a given image? And it's basically composed of two terms. One which just asks that we preserve information. You could sort of come up with a number of different metrics here, but usually we use the squared error of how well our model is matching the incoming data coming in. But this is the most important part, is that we impose a penalty on activities. And typically this is something like an L1 cost function, but there are many others that also work. But it just cannot be quadratic. Okay, so we typically use let's just like the absolute value of these coefficients as the penalty. Okay, so then the coefficients are computed by actually minimizing this energy function. So given you have a dictionary that someone has given you, if you already learned, then for the image coming in, you compute the coefficients for that image by finding a minimum of this energy function, because when this is L1 or absolute value, there's not an analytical solution to this. It has to be computed numerically or iteratively in a neural circuit. And so what we showed later is that you can actually design a neural circuit that can do this, that can exactly minimize this function, this energy function, and that's shown here. So each of these neurons in the system is driven by computing the inner product between each of those features and the image, and that basically provides the feed-forward drive to a neuron, and then it receives inhibitory input from other neurons, and the strength of that inhibitory input is proportional to the overlap between the basis functions of the features of those different neurons. Okay, and then each of these neurons goes through a ReLU, nonlinearity in this case. So in the stuff I'm going to be talking about from here on out, hopefully, they're not going to be consistent, but most of the stuff I'm going to be talking about, we're going to be imposing positivity on the coefficients. So we're going to assuming all these coefficients to be strictly positive. In the past, we've let them be both positive and negative, but here we're going to be moving in the train where they're imposed to be strictly positive. Okay, so when they're strictly positive, it turns out that putting those through a ReLU nonlinearity exactly minimizes that energy function when the cost function on the coefficient activities is just the absolute value, or just proportional to the activity value. Okay, and then that parameter lambda in the cost function determines the threshold of the ReLU. Okay. And what's kind of remarkable about this is this circuit is exactly a Hopfield network. Okay, so these are just, for those of you who know the Hopfield network, this is exactly the Hopfield dynamics. The only difference is that we're using a ReLU here instead of tanh. Okay, so when you put ReLUs here, it does sparse coding when this G matrix is proportional to is equal to the gram matrix of your dictionary, and the feed-forward drive to the system is just equal to the inner products of your features with the input. Okay, so that is to say that you can do this in sort of a realistic way. You can run this system in real time, and as you provide a time-varying input here, this system can track and provide in real time a stable solution to solution to that energy function in real time. Okay, to compute a sparse representation of the input as it comes in. All right, so when you learn the dictionary, this is sort of a well-known result by now that they come out to be localized, oriented, and bandpass similar to V1 neurons. But then most importantly, I mean, people always say this and they say, oh wow, anything gives you Gabors. First of all, that's not true. The second thing that's really important is the most important part of this result is how the dictionary tiles the space. It's not that you sort of just look at these and you have like a zoo of functions. These functions tile the space in a very interesting way. They tile it like a wavelet. Okay, so this is interesting and makes connections to the engineering community because people use wavelets for image compression. They're known to provide sparse representations of images. They provide a frame, a complete representation of image data. And so the way they tile the space is really the most important part of what you get out of this kind of optimization strategy, not just how they look per se. Okay. So that's just a few notes about that. All right. So,
Excuse me.
yeah.
I have a quick question.
Yeah.
If the input image happens to have all of its information direct at the edges or boundaries of those tiles,
Yeah. Well,
what happens?
it's this. We're sort of. This is sort of a toy model, right, in the sense where we're sort of assuming that this population of neurons is only looking at stuff in this box, and really what we're going to have is a system of neurons that are tiling the whole image, and there's no boxes there, right? So.
I'm really trying to get to what's the effect of the choice of the dictionary elements.
We don't choose them, we learn them. Okay, so they can be anything they want to be within this box. So if all the data were falling along the perimeter of that box, then those dictionary elements would go and code the perimeter of the box. Okay, but this is learned from the input data, and because the statistics are stationary and kind of homogeneous over that array, it doesn't matter how big we could do this on 32 by 32 batches or whatever, you would get more or less the same solution. Okay, so now we can sort of look at how that system codes a time-varying image. We're just providing here an input patch that's, it's sort of a snippet from a movie, and there's a larger image here that's changing, right? And we're just looking at one local part of that movie changing over time. This is the sparse encoding of the image, and just as the reconstruction, just showing we can get our information back. So here it is the image data coming in. We're pushing it into a higher dimensional space, coding it sparsely, and it provides a complete description of everything that's happening here, okay? So it's sparse, that's good, right? We like that idea. But, when you sort of look at this, it's like, is that helpful? It sort of looks bewildering, and it's not clear what's going on. And that's because these coefficients are essentially unordered. Okay, we just have a list of coefficients here corresponding to that list of dictionary elements we learned, and so that's why it kind of looks bewildering and perplexing. But if we take those coefficients and now order them, if we look at specific pairs, we see something quite different. So this is a very much simpler movie. This is just an edge moving back and forth. And now what we're doing, this is just showing a bar chart of all those coefficients. I'm sorry, here they're going positive and negative, so hopefully flipping back and forth. But okay, so these are just a bar chart of the coefficients going up and down like we were like we were showing before. So this doesn't make much sense. But now if we take specific pairs of these dictionary elements, so two units that have similar orientations nearby, is what we're showing here, but you could also take two units that have sort of different orientations as well. Then you get these interesting profiles of activity where you see in the joint state space, they're moving through smooth trajectories. Okay, so there's something interesting going on here, and if you organize it correctly, you can start to make sense of this activity and what it means. That as you move along this trajectory, that sort of represents the fact that the edge is moving back and forth. Okay, it's good. It gives you a more explicit representation of that. Yeah.
You're going to kind of have to move along trajectories. What's the surprise? The fact they're smooth, or?
I'm sorry?
If you change these stimulus continually, they'll move along some trajectories, right? That's kind of has to be the case, or no?
Well, that's what I'm getting at. Yes, you're right. I mean, to some people this is obvious, but some people look at this and they say, "Oh, gee, that doesn't look very smooth." Okay, and I'm just trying.
Sort of apply to anything that's continuous in time. It sweeps out the trajectory, and if you're periodic.
In the joint state space, right? That's kind of what I'm getting at. And if you just looked at a disconnected pair, if I just took two pairs at random, this wouldn't look like a smooth. It was just like you'd see something go up down here, something go back and forth here.
Smooth, it just wouldn't have a nice.
Okay, fine. I see what you're saying. Smooth is not the right word. Okay, curved trajectories.
Kind of cool shape is really what you.
Cool shape, yes, yes. Much better scientific term there, right? Cool shapes. Okay, and here's another cool shape. So here's the sort of conceptualization of what's going on, right? In this joint state space, that what's really happening is that there's this low-dimensional manifold that images are moving upon. Okay, so the space is very sparse. We know that natural images occupy a very small fraction of the state space of all possible images. There's lots of ways to show this. But moreover, we know that is continuous and connected. Okay, it lies along a low-dimensional manifold. So this is just a kind of fanciful depiction of what that looks like. Okay, when we do sparse coding, what we're doing is by virtue of imposing sparsity, we're forcing the basis vectors of the transform to point towards the data, right? They have to point towards the manifold. Okay, and then so they do that in such a way that they can code points in between by adding together, by forming linear subspaces, okay? So this is why the basis functions that you learn kind of look like Gabors, because Gabors are modulated sine waves, and sine waves are functions such that when you add them together, they shift, okay? So this is one way of understanding the kind of solution that you get out, is basically learning a good set of interpolating functions from moving along this manifold. What we want to do now is make that explicit. As you move along the manifold, we don't want to have just coefficients that are kind of bumping up and down. We want to have something that tells us we're moving along the manifold. Okay? So this is what leads us to the idea of manifold flattening. Okay? And this is, I would argue, a very important concept and idea that occurs in sensory coding of the system. And just like sparse coding is informed just about these representations, so will these ideas of manifold flattening. Okay? So when we talk about manifolds, one immediately thinks of a Swiss roll, right? And so there was this early work that came out, not early now, I guess in 2000s. To me, this is still recent, but some of you in the room were probably born when this paper came out. But so this is really exciting when this work came out, showing you how you could learn manifold models of data. And this is just showing a bunch of data in a three-dimensional space. So these are all little data points, and these data points happen to lie along a sort of a curved manifold that folds in itself like a Swiss roll. And so obviously, if you applied a PCA to the space, to this data, it would basically be useless. It wouldn't tell you anything. Moreover, if you applied sparse coding to this data, or ICA, it wouldn't do anything for you. Okay? So somehow you have to do a nonlinear transform to get into the coordinates of this manifold. Okay, so they developed some algorithms, and I'll talk about one in a second, for how to take this kind of a manifold and flatten it. Okay, so that's the goal, is to take this data. If you have data coming in that looks like this, the argued goal now is to get into a space where my neurons are representing these coordinates here, and the space is now flattened. So this is how LLE does it. I'm just going to go through this because it's very sort of a foundational sort of to how we're approaching the problem here. So the way LLE works is that you have all these different data points along your Swiss roll, and now you take for each data point on your manifold, you form you find its nearest neighbors first of all. So that's a data point in question, xi. That's a specific data point in the high dimensional space, and you find its nearest neighbors in the high dimensional space, which are presumably nearby on the manifold. And now what you do is you form a linear reconstruction of that data point from your nearest neighbors. Okay, and you do that by computing the weights, the interpolation weights. These are forced to sum to 1. So you compute these interpolation weights from the other data points. So this is sum over j not equal to I. Okay? It's over these other data points. So you basically form a locally linear approximation of any given data point in terms of its neighboring data points. Okay, so that's the first step in LLE. It's a locally linear approximation. That should remind you what we just talked about. That's what sparse coding is kind of doing, a locally linear approximation, right? And so the next step is to compute then embedding. And the idea in the embedding is now you want to compute the coordinates of the corresponding coordinates of these points x in a lower dimensional space. So here we're in a high dimensional space, and now we want to map down to something like a two-dimensional space, in the case of the Swiss roll, in a two-dimensional space. And for each data point x here, we have a corresponding data point y here, mapped into the embedded space. And the goal is in the embedded space, and now we're in the lower dimensional y space, we want the same interpolation strategy to hold. Okay, so the idea here is that we want any given data point, the embedding coordinate y, point y, to be linearly approximated by its neighbors. Okay, and we're going to use the same weights, using the exact same weights. Okay, so using the same weights we computed up here, then the idea is now in this system here we were computing the weights that minimize this expression, and this expression here, given the weights, we're computing the coordinates y. Okay, this is the objective function for computing the embedding. This is how we compute the coordinates, the corresponding coordinates of our data and points in the manifold, is by minimizing this function with respect to the y's. Okay? And that could be basically formed as a minimum eigenvalue problem. Okay, so that's the way that works. And so now this is not particularly efficient because you're using your entire data set as the model of the manifold. So if I give you a new data point, then basically your strategy for finding out where it is on the manifold is to ask, well, in my entire data set of like 1,000 data points or whatever, who are my nearest neighbors, who have I seen before, and then interpolate between those. So it's basically, your manifold mapping strategy is table lookup, right? So you'd like something more efficient than that. And then so that leads us to this idea of LLL, locally linear landmarks. And so locally linear landmarks, the goal is the same, to flatten the manifold. But the idea is now we're going to tile this manifold not with the entire data set as our dictionary, but with a much smaller set of landmarks. Okay, so this much smaller set of landmarks, it could just be a subset of our data, or they could be learned. Okay, And now we're going to approximate each of these data points in terms of a linear interpolation between these locally linear landmarks. And these landmarks are much fewer than the number of data points. So whereas we may have 1 million data points, maybe there's only 1,000 or maybe only 100 of these landmarks X. Okay? So now the idea is if we can find a mapping between our dictionary elements, phi, so we can think of these landmarks in our manifold as dictionary elements, just like in sparse coding. And if we can find an embedding from our dictionary elements into this lower dimensional space, then our embedding strategy is extremely simple and remarkable. It basically says, for each data point, if I hand you a new data point along this manifold, compute its sparse code using this dictionary of landmarks. Okay, so compute its sparse code alpha. So I'm going to give you some data point X, find its sparse code alpha, right? That's basically going to try to grab the nearest neighbors to it on the manifold and do a locally linear approximation of it. And then its coordinates on the manifold are given by, remarkably, a linear projection of those sparse coefficients. Okay, so the new sparse coding strategy, the new manifold mapping algorithm then is compute a sparse code and linearly project and linearly collapse into a lower dimensional space to find its coordinates.
So phi is a vector this time?
I'm sorry?
Phi is a vector?
Phi is a dictionary. It's a matrix, just like before. The columns of phi are each column of phi is a landmark on the manifold. So it's your dictionary. Yeah.
Why is alpha sparsely selecting the neighbors instead of ones that are far away that happen?
I'm making a bit of a leap here. Okay, so it doesn't work that well for the Swiss manifold. It turns out it's for the Swiss roll. But in general, it's going to work in higher dimensional space. Okay, you can sort of rely upon the sparsity principle to kind of weed out and pull your nearest neighbors. Okay. All right. So now there's one thing last thing I have to convey, which is that what we've been talking about up to now in these manifold models is the idea of a one sparse function of the manifold. Okay. So it's the idea of simply having a simple delta function, and the idea of them when we have these manifold is that, like the Swiss roll, is that I give you a certain data point where you're at one point along that manifold, right? You're just occupying one point. So we could think of basically the function on the manifold as like a delta function. We're just sort of sitting at some point, and I'm sort of moving that delta function along the manifold. So we could think of it as a one sparse function on the manifold, and we're doing a locally linear interpolation in terms of its nearest neighbors. And so now we're going to generalize to thinking of a k-sparse function of the manifold. Okay, so instead of just thinking about being at a single point, I could be at multiple points. Okay, so I have sort of k delta functions sitting on this manifold, and now I want to do a locally linear approximation of them. So it leads us to this picture down here. So there's two things we're changing now. Is one, instead of using the whole data set as our dictionary, we're using a set of pruned out landmarks that we're going to learn to capture the manifold, so many fewer landmarks. And the second is that instead of representing a single point, okay, a delta function on the manifold, we're going to have a sparse function on the manifold. Okay, so in this case, 3 different delta functions on the manifold. Okay, so now we're ready to look at this picture. Oh boy. Okay, now we're ready to end the talk, I guess. But now we're ready to look at this picture and understand what it means. And this is basically the topographic ICA. And so in topographic ICA, you learn a dictionary in which the dictionary elements are ordered. Okay? And so the way they do it is by imposing an ordering in advance. So for each unit, you tell it that these are going to be your neighbors. You impose a topology, and so in this case, a 2D topology. And you say that you will be most correlated to your neighbors, basically. Okay? And then the dictionary grows into that solution. And so the way we can think about this is that when we get a representation in this format, we're going to get a sparse representation using this dictionary. But now that sparse representation is going to be spatially organized into a 2-dimensional map. Okay? And so if I give you an image, it's going to show up as some sparse pattern here as a collection of sparse bumps. You're going to see little clusters of activity and sparse bumps on this manifold. Okay, and that leads us to this paper, which is, in my view, one of the most important papers in natural scene statistics, this paper by Apo Huvarinen, curiously entitled Bubbles. And the idea of bubbles is just this idea we're talking about, that you have sort of local clumps of activity on this 2-dimensional manifold, in this case, in topographic ICA. But then it really begs the question of, well, why 2-dimensional, right? Well, they just did 2-dimensional because that's something you can look at. Maybe it should be a 3D manifold. Maybe it should be a 4D manifold. Okay, so we really want to learn that. Okay, and so this brings us to Yubei Chen's PhD thesis and this idea of the sparse manifold transform, which is as follows, that we're going to think about sparse coding now, the process of sparse coding. Normally, we just get a collection of unordered coefficients representing our signal. So this is some image coming in, and we get some unordered list of coefficient activities, and we're going to think about them being now organized on a lower dimensional manifold. And we can compute an embedding of each of these dictionary elements to some coordinates. So each of these dictionary elements, phi, has some embedding p. These different p's are on this manifold. Okay, and now when we do that, what we'll see is that these coefficients, which were all activities, which are all kind of unordered here, we'll see them showing up as kind of local clusters on this lower dimensional manifold. And we could think of each of these bumps as having like a center of mass to it. Okay, and we can code those bumps by their center of mass, which is these red delta functions here. Okay, so we can think of, in this case, an underlying 3 sparse function coding the signal, and then reconstruct from that. Okay, so the question is, how do we learn this embedding? How do we learn to embed these basis functions here onto the manifold? And that the final part here is the idea of persistence. Then this is where the idea of persistence comes in to learn this. And so what we desire is that in the manifold space things are flat. Okay, so in the data space things are curved. As we move along the manifold, we're moving along the curve in the space. But once we've successfully mapped the manifold, we want things to be straight. What's the mathematical sign that things are straight? Well, it's just that if I do linear interpolation, then I should be able, between 2 points, then the point that I land at in between should also be on the manifold. That's not going to be true. If I try to linearly interpolate between that point and that point, I'm not going to be on the manifold. Okay, so I want to stay on the manifold. So this is our objective function, is basically to minimize the second derivative in the space of these trajectories. Okay, so having done that, I'm in a position then to summarize. This is the sparse manifold transform. It basically can be encapsulated as follows. We start with data. We compute its sparse code. We compute an embedding of the dictionary P into this lower dimensional space, and then using that embedding, we project these sparse coefficients into this lower dimensional space. It's invertible. So from this lower dimensional representation up here, we can get back to our higher dimensional sparse representation, and in turn, would be a sparse approximation, and in turn back to our image. So the red arrows indicate basically the computation would be the process of sparse inference, and the green arrows the process of linear collapse or linear projection. Okay. We have a simple example here on the 2D disk. I'm going to have to skip that. Okay, so I'm just going to cut to the chase and show you a result on video, and this is just showing results here. So a video sequence here, a little image patch moving along. This is as reconstruction over here on the right. So up here is shown the sparse encoding of that video patch. So it's just like a bunch of little twinkling coefficients, unordered as before. And this is the manifold embedding of that space. So this is not ordered because all we're doing is we're computing a projection into this lower dimensional space beta. So it's not yet ordered. But basically what you can see, the thing we want to convey here, is that we've taken very, very fast changing activities here, and it's much represented as, if we can sort of look at in the joint space, we would want to see more linearized trajectories, basically slower changing activity and lower dimensional. Okay, that we've sort of been able to sort of capture, get into the manifold coordinates, and then from this we can actually go back, reconstruct the coefficients, and at least partially reconstruct the image patch. This transform is stackable, so that we can actually stack it in a hierarchy. So once you've computed this embedding beta of the sparse representation, now we can learn dictionaries again on this embedded space, and recollapse into a lower dimensional manifold again, and so forth. Okay, so I'm not going to have time to go into those results. Maybe we can talk about them at a discussion. But the message I guess I want to leave you with is what we're sort of thinking about here in terms of mapping this idea onto the cortex. And this it sort of ties back to this diagram, but also these ideas that Cox and DiCarlo talked about in terms of thinking about the ventral stream as doing progressive manifold flattening. So in the image space, if you look at, or something like V1, which is more tied to the image space, if you look at these representations, we'd find these manifolds entangled in the sense that as objects move through the world, they're moving through this space in very quite complicated ways. We'd see these activities changing very quickly over time. And we could sort of think about these transformations that are occurring along this stream as trying to progressively flatten these manifolds. And what we're proposing here is an algorithm, basically a neural computation for flattening these manifolds that's composed of 2 very simple strategies. One is dimensionality expansion by sparse coding, followed by linear projection into a lower dimensional space. So the idea is that each of these stages, you're not doing a complete flattening. It's kind of you're doing a little bit of flattening, right? And then you do it again, and you're better, right? Along the way. Okay, so So I had to go through a lot of that fast towards the end, but the basic ideas that we're trying to convey here is that we found a link between this idea of sparse coding and manifold learning. We can think of sparse coding as providing a foundation for doing manifold learning. And this idea of temporal persistence in the structure of visual data can be exploited to learn these embeddings of the dictionary into a lower dimensional space to flatten the manifold. And that, that this process of flattening, manifold flattening can be accomplished in successive stages of dimensionality expansion by sparse coding and dimensionality collapse. All right, so that you've been all very silent. So happy to take questions if there's time. Yeah, Sophie.
So in terms of reconstruction performance, how does it compare to compressed sensing? Well, I guess it's not the point, but...
That's not really the point, but so much in terms of, it's interesting. So something we definitely want to investigate more is like because there's obviously like a compression occurring here, and we want to sort of see about that. But the way it would differ from compressed sensing is that in compressed sensing you typically use like a random projection matrix, right? So it's completely unrelated to the structure of the data, and it's not going to have in general this flattening property. So here we're looking for a very specific projection. So it's related in the sense that protecting something sparse, projecting the lower dimensional space, and we can get back because of the sparsity. But in this particular case, it's a special projection matrix that gives this flattening idea.
Bruno, you started out saying that the point of the visual systems is to reformat the visual signal progressively so that it's more useful, or that's one of the things you said. And I think that's one of the things you believe. So this is a stackable system. You've made one stack on top of what what you started with. Can you comment on how you reformatted the representation? Not in mathematical terms, but I looked like the pictures that you briefly showed still appeared to be kind of oriented. I mean, I don't know if you were trying to represent receptive field properties to the extent you can even talk about that.
This here?
Right. So these appear to be oriented filters, Gabor-like filters. And I'm just wondering, have you reformatted the visual image in a format that is more useful for behavior compared to what you started with? And I'm not seeing that there.
Here. Still early days. I agree. I'm not entirely, I think I should let Yube speak to this as well. So we've been applying this more recently to MNIST, and we sort of do see more sort of higher degrees of abstraction occurring here. But maybe I'll let Yube speak to that.
Basically, if you apply this to different data set, for example, to image, to MNIST, for example, and you start with like a 32 by 32, or 28 by 28 in this case, the image patch. And the first layer you do sparse coding expansion, very overcomplete, and you see very small strokes, like a small curve for each of the numbers. And then you go to the next layer, you collapse, and learn sparse coding again. Right, do this stage. And the stage 2 basis function will look like much longer, much larger parts, like strokes, longer strokes. And along the way, you can actually probe their neighbors in this in their embedded space at each of the layers. Right, the first layers contain different small strokes, and their neighbors are all small strokes, like a six, a small part. And its neighbors in the embedded space are all like the small strokes. And then in this layer 2. The longer strokes as neighbors are also longer strokes in this layer, and then you go up into the layer 3, and you see almost one number and a different number, but much larger.
Something I want to emphasize about what you're looking here is, again, like when we look at these things, one shouldn't just look at the basis functions per se. It's about how they tile the space. And the main point here is just compare this number up here. We only have 200 of these features up here. We have 4,000 of these down here, right? So these functions have to tile very specifically in each and every location. These are tiling space extremely coarsely, right? And so the beauty of this is that the way these combine, if you want to shift that edge, you just add it together with another edge, and that other edge might be over here, right? And so with a much smaller dictionary, you're getting much more leverage out of it. Okay, there's a little bit of sort of more complexity going on here. I agree, it's rather modest right now, but I think the main thing I think that I find impressive is that this dictionary is much more compact, and it's more richly structured, and still a lower dimensionality set, and providing you something close to a complete description of the image data. You don't seem satisfied, but it's okay. Yeah.
It's not clear why MNIST is an unnatural data set,
Yeah.
and you've used a natural data set. And I'm not, so I would have leaned towards seeing what the results were on the natural data set compared to MNIST, which is very, very, simplified. And secondly, when you don't really want the necessarily, or if the result is that at the top, after stacking these, we get units that are more like templates of individual stimuli, that also is not a terribly satisfying new revelation. So I'm trying to figure out if you are achieving re-representation. You're not really training this to do something useful. You're trying to still capture statistics efficiently of the input.
They're trying to do manifold flattening. Right. And the claim is we have evidence, we can show you are definitely much more flattened up here than you are down here. And so that's, number one. In terms of these specific dictionary elements, I mean, again, I just would put some caution. It's still early days. Ask me next year or next month, hopefully. Well, yeah, anyways, yeah. Maybe in the back, yeah. So
this notion that the dictionary basically gets gradually smaller, isn't it true also for something like the autoencoder?
It's a kind of autoencoder. It's like a kind of basically, sparse coding is an autoencoder. But we're basically doing this with this extra constraint beyond just sparsity, but of flattening.
I'm trying to contrast it basically with, say, Hinton's autoencoder, basically. Of course, the math is different, but... I guess, what I've tried to give here is a theory behind how you get there, right? Rather than just sort of stacking a bunch of ReLU units and crossing your fingers and hoping something amazing happens. We're trying to say, look, here are the elements. This is, based on the structure of the data and the mathematics of how you flatten manifold. Here's a way to do it, right? And it has kind of a similar structure to that in the end. But one of the main differences is the sparse inference, doing sparse inference in between, as opposed to just computing linear projections and thresholding. But they're sort of related in that sense that they both have those elements. But yeah.
So I'm trying to match this up with how these transforms might be computed in the brain. Is this all biologically plausible, and you have a good idea what sort of brain network might do this?
Okay.
And the next step for me, of course, would be then how to write that as a neural network model.
Right. So right now I guess it's all kind of loosely biologically plausible in some sense. This is the LCA circuit. The way to compute the sparse code is something that you could do in a local circuit of interconnected neurons. Okay, that maps very well onto a circuit like layer 4 of V1 or something like that. You could imagine that happening. Okay, the idea of linear projection, that's what could be simpler. So I don't see anything that, I mean, if anything, it's too simple to map onto the cortex. I think so. Then that would be looking sort of richer things that you would need here. Yeah.
I'm trying to extract from this theory what would be consequences for use of brain computation. And I would guess, for example, that simply by having now this manifold representation, many now predictions or kind of classifications can be done with simple linear readouts or simple linear prediction mechanism, right? And sometimes you choose a representation which makes computational operations much simpler than...
That's the whole idea, right? I mean, once you're in this kind of space, then, classification is trivial, right? Yeah. But here it's very hard. Yeah.
So I have a question about how you would evaluate this model. Once you have a nice stacked version of it and you have a variety of things, would you use some proxy to likelihood? Would you qualitatively look at the responses of the filters and, the various layers? So how do you get a quantitative, in some sense, measure of quality out of this?
Yeah, great question. I mean, there's lots of measures one could use. Right now, we're focusing on the idea of flattening. So I would sort of say, how flat is it, and still preserving information. So it's sparse. I like that part. Now I want it to be flat. So, hooray. But now, sort of, what degree of abstraction have we achieved? And then maybe now applying this to some task. Compression would be something I think could be very interesting for video to try this for that. So I think there's a number of different sort of quantitative evaluation avenues to take. It's still early days, but for right now I'm just trying to, this is like the first complete talk I've given on this work, and but that's kind of where things are. So yeah, I'm sorry, next to you. You haven't asked a question yet, yeah.
So basically I think the goal is somehow to get some kind of abstract representation of your input, right? And then that would mean to me that you want to kind of throw away information, kind of the stuff that's not interesting. Like But if you do reconstruction, you always try to reconstruct, all the details. So I wonder, did you think about that? Is there some way to?
I love reconstructing details. I don't think there's anything wrong with that. So this idea that you have to throw away information, it's obviously true, in some sense, but on the other hand, the biology has gone to great effort to design photoreceptors to do single photon detection. Right, and so there's all this stuff happening on the retina to take information and handle it very precisely. That's data about the world, and I sort of take the idea that every photon counts, and the detail you're getting is mainly in the fovea, right? So where you're looking is where the detail is, and you're grabbing that detail, and you have short-term awareness. Once you move your eyes, that detail's gone, okay? And you can't use it for something. But in the moment, if you're trying to reach for something and sort of pick up a hair of the carpet with tweezers, you need that detail, right? So I guess sort of taken. I think you want degrees of abstraction. So you want maybe information to be sort of thrown away as you go along, and the complete representation of the stimulus is going to be all of these areas together, right? This is going to sort of have the abstract parts, and this is going to have the details or something like that. But the whole system together, I think you do want to model everything.
Well, I think
Yeah, please.
Actually, if you compress, of course, you store away information. The key here is the sparsity, right? For example, if you only have one edge, you can coercify the variational space, transformational space, and just use two numbers. But what if you have two edges in between, just very close to each other? In this case, when you go up to the higher layer representation and go back, you collapse them into one edge. Just like we can show that hierarchical manifold interpolation in a sense in the layer 3, you have one edge here, one edge here, and they have absolutely no overlap. And you interpolate in layer 3 and go do the inverse transform. What you see is the edge in between, not two edges. So that, in that sense, that's the loss of information.
It depends on the sparsity of your code.
Actually, exactly. There is a loss going on here. I didn't get into it, but yeah. So Antonina.
How would you construct multimodal representations when you have a manifold, say, detect only visual stuff and manifold on auditory? How would you combine them together using this flattened representation?
Yeah, great question. I think ultimately, right, because the visual and the auditory, they correspond to the same thing in the world, right? And there's sort of some common manifold that encompasses those. This is like a Kevin O'Regan question. And ultimately, I think that's where you'd want to get. It's too far from where I can see with my binoculars right now, but but I think that's, okay.
One last question, and then
Okay.
we can address some of
Yeah.
So I wonder if it's possible to reconcile the details versus compression if instead of trying to reconstruct an image from your sparse representation, right, you try to reconstruct an image, the next image, sort of like in predictive coding.
Yeah.
And then if in a movie, in your example, you said we're picking up a hair with tweezers, presumably it still stays there, and that's important. I'm focused on it, and it's not moving, right? But the leaves of the tree in the wind, they move, and I really don't care about them that much, right? So I wonder if it's possible to take it sort of seriously and try to reconstruct receptive fields for the next frame, right?
Absolutely. I think there's a way to do that, because now that you're in this sort of flattened representation, things are more predictable. It's easier to predict with a sort of trivial computation. And this is something that Yubei has done some early experiments with, is using then the second derivative to regularize the sparse representation, right? So given I've seen frame 1 and frame 2, I expect this on frame 3, right? And so to use that to regularize the sparse representation. Right. Okay, thanks.